So two methyl groups, it is having a common name dimethyl ether, and the IUPAC name is methoxymethane. When sodium alkoxide is heated with alkyl halide in alcoholic medium, ether is formed based on SN2 mechanism. So this reaction is called Williamson's ether synthesis. So diethyl ether and ethyl methyl ethers are usually gases, and all other ethers will be in a colorless liquid form. Hello dear students, I am Roja, your chemistry lecturer from Vidhyaashram PU College, the Temple of Excellence, Mysuru. So let us start the chapter Alcohols, Phenols and Ether. So in the previous session, we have studied about physical properties and chemical properties of phenol and also their uses. So in this session, we are going to study about ethers, classification of ethers, then nomenclature of ethers, and also about methods of preparation. So let's start with what are ethers and what is the general formula of ethers. So ethers are alkoxy or aryl oxy derivatives of hydrocarbons, and the general formula of ether is ROR dash, wherein R and R dash are alkyl or aryl groups. So classification of ethers are as such, that is, first one is simple or symmetrical ethers. The ethers in which oxygen atom is bonded to two identical alkyl or it can be aryl groups are called simple or symmetrical ethers. For example, diethyl ether, wherein oxygen is in between and on the either side it is the same compound C2H5 and C2H5. So it is diethyl ether and it belongs to symmetrical ethers. The second example, diphenyl ether, wherein it consists of C6H5O, C6H5O. So R and R dash are same group, so therefore it belongs to simple or symmetrical ethers. So the second one is mixed or unsymmetrical ethers, wherein the ethers in which oxygen atom is bonded to two different alkyl or aryl groups are called mixed or unsymmetrical ethers. For example, ethyl mether ether. So here CH3O C2H5, here R is a different methyl group and C2H5 is a ethyl group. So both are different groups. And in the second example, that is anisole, that is CH3O C6H5. So this is alkyl group, this is aryl group. So they are two different alkyl or aryl groups. Next is nomenclature of ethers. So in common system, ethers are named by adding suffix ether after naming the alkyl or aryl groups in the alphabetical order. But in IUPAC systems, ethers are named as alkoxy derivatives of alkanes. So let us see with the examples. But for mixed ethers, the large alkyl group is selected as parent alkane. So here are the some of the example. Let us see one by one. So first compound is CH3O CH3. So two methyl groups, it is having a common name dimethyl ether, and the IUPAC name is methoxymethane. So second one is C2H5O C2H5. So it is having a common name diethyl ether and IUPAC name is ethoxyethane. Next is CH3O, CH2, CH2, CH3. So this is a different compound. So the compound name is methyl N-propyl ether and IUPAC name for this compound is 1-methoxypropane. Next is C6H5O, CH3. So it is having a common name anisole, but IUPAC name says methoxybenzene. Next is C6H5O, CH3, CH3. So it is having a common name ethyl phenyl ether, but the IUPAC name is ethoxybenzene. Next is C6H5O, CH2 6 times CH3. Therefore, it is having a common name heptyl phenyl ether and IUPAC name is 1-phenoxyheptane. So next is structure of ether functional group. So in ethers, two bond pairs and two lone pairs of electrons around oxygen are arranged almost in a tetrahedral arrangement. So the CO-C bond angle, that is 111.7 degree, that is in methoxymethane, is slightly greater than the tetrahedral angle, that is around 109 degree 28 due to the repulsive interaction between two bulky groups. So the CO bond length, that is around 141 picometer in ethers is almost same as the bond length in alcohols, which is having 142 picometer in methanol. So here is a structure wherein oxygen atom in between the alkyl groups will have a bond angle 111.7 degree, and the bond length between carbon and oxygen is around 141 picometer. So this is an example of methoxymethane. So next is about methods of preparation of ethers. So first one is dehydration of alcohols. Alcohols undergo dehydration in the presence of concentrated sulfuric acid. So the formation of product depends on the experimental conditions. When excess of alcohol is heated at 413 Kelvin in the presence of concentrated sulfuric acid, so ethers are formed. So here is a general equation: alcohol plus another molecule of alcohol in the presence of concentrated sulfuric acid at 413 Kelvin. So it can yield to form ether along with water molecule. So hence ethers are called anhydrides of monohydric alcohols. Monohydric alcohols are nothing but alcoholic group. It will be one in a methyl group attached to it. Example, when excess of ethyl alcohol is heated with concentrated sulfuric acid under same condition, so diethyl ether, or it can have a name, ethoxyethane is termed. That is ethyl alcohol, that is two molecules of ethyl alcohol in the presence of concentrated sulfuric acid at the same condition. So it would form diethyl ether. So next, this method is suitable only for the preparation of simple ethers by primary alcohols. Why is it called primary alcohols? Because hydroxyl group is only one time present in the compound. So therefore it is primary alcohols. So when the alcohol is secondary or tertiary, elimination takes place instead of substitution to give alkenes. So second one is Williamson's ether synthesis. When sodium alkoxide is heated with alkyl halide in alcoholic medium, ether is formed based on SN2 mechanism. So this reaction is called Williamson's ether synthesis. So here is a general equation wherein sodium alkoxide plus alkyl halide under SN2 mechanism, it would provide ether plus sodium halide. Next, let us see with an example. When sodium methoxide in alcohol is heated with methyl iodide, what is the product that we get is dimethyl ether is formed. So here is a sodium methoxide which reacts with methyl iodide. Under SN2 mechanism, it is going to produce dimethyl ether. This method is useful for the preparation of ethers containing substituted alkyl groups, whether it's in a secondary or tertiary alkyl groups. So the reaction involves is SN2 that attacks an alkoxide ion on a primary alkyl halide. So in this method, better results are obtained if the alkyl halide is primary. It shouldn't be a secondary or tertiary. Alkyl aryl ethers can be prepared by treating sodium phenoxide with alkyl halide. So let us see with the example, that is when sodium phenoxide is heated with methyl iodide, methyl phenyl ether is formed. So methyl phenyl ether is nothing but anisole. So here is a sodium phenate reacting with methyl halide to give anisole compound plus sodium halide under SN2 mechanism. So let us see now the physical properties of ethers. So diethyl ether and ethyl methyl ethers are usually gases, and all other ethers will be in a colorless liquid form. So the bond between the oxygen atom and the carbon atom of the alkyl group in an ether molecule are polarized. That is due to difference in electronegativities between carbon and oxygen. So that is why the reason for the polarization is due to the difference in the electronegativities of carbon and oxygen bond. Since carbon and oxygen bond is polar in nature, ethers possesses a net dipole moment even if they are symmetrical. So the dipole moment of dimethyl ether is 1.3 dBA and dipole moment of diethyl ether is 1.18 dBA. The weak polarity of ethers do not appreciably affect their boiling points, which are comparable to those of the alkanes of comparable molecular masses, but are much lower than the boiling points of alcohols as shown in the following cases. So here are three compounds taken as an example: N-pentane, ethoxyethane, butane 1-ol. So here the boiling points are slightly differed from each other. So that is N-pentane has 309.1 Kelvin, ethoxyethane has 307.6 Kelvin, and butane 1-ol has 390 Kelvin. Next, the large difference in boiling points of alcohols and ethers is due to the presence of hydrogen bonding in alcohols. That is, it can be intra or inter hydrogen bonding. So here, what is the type of bonding involved? Let us see. Lower ethers are miscible in water to some extent, probably around 7.5 grams per 100 ml of water in case of ethoxyethane. So this is due to the formation of hydrogen bonds with the water molecule. So this is a water molecule and this will be a ether. So there is a bond between electronegative atom of oxygen and the hydrogen. So this is responsible for being a polar in nature. The solubility decreases with increase in the number of carbon atoms in the compound. So the relative increase in the hydrocarbon portion of the molecule decreases the tendency of hydrogen bond formation. So ethers are appreciably soluble in organic solvents like alcohol, benzene, etc. Next, let us know about chemical properties of ethers. So chemically, ethers are less reactive. So the low reactivity of ethers is due to the absence of the active site in its functional group. It is not like phenol group. So however, under specific conditions, ethers undergo some chemical reactions. Let us see what are those chemical reactions. So here it involves reaction involving cleavage of carbon-oxygen bond. Let us see. When ethers are heated with limited amount of hydrogen halide, mixture of alcohol and alkyl halide is formed. Here is an example, that is diethyl ether. In the presence of hydrogen halide, it is going to give a mixture of alcohol along with that alkyl halide. So here ethanol and ethyl iodide are formed. Next, when ethers are heated with excess amount of hydrogen halide, alkyl halides are formed. Only alkyl halide is going to form, not a mixture of alcohol and alkyl halide. So general equation is shown here, and the example that we have taken is diethyl ether in the presence of excess of alkyl halide, so it gives ethyl iodide. The order of reactivity of hydrogen halide is as such. So hydrogen iodide is greater than hydrogen bromide, which is again greater than hydrogen chloride. So when hydrogen iodide reacts with unsymmetrical ether, the iodine attaches to the smallest alkyl group. So here N-butyl methyl ether is taken. So this side of the portion is having a bulkier alkyl group and this is the smallest alkyl group. So what happens here is iodide ion will attack the smallest alkyl group, not the bulkier one, to form N-butyl alcohol plus methyl iodide. So next, however, when one of the alkyl group is a tertiary group, then the halide formed is a tertiary halide. So if this is a tertiary molecule, that is third butyl methyl ether, then the product formed will also be in a tertiary form. That is third butyl methyl ether reacts with HI to give third butyl iodide with alcohol group, that is methanol. Next, alkyl aryl ethers react with hydrogen halide to form phenol and alkyl halide. So the product that we get is here phenol. So that is alkyl aryl ether reacting with hydrogen halide. So it is going to give phenol along with that alkyl halide. It's a mixture of phenol and then alkyl halide. During this reaction, alkyl oxygen bond is cleaved. This is due to more stability of aryl oxygen bond due to partial double bond character. So here is a partial double bond character between oxygen and the aryl group. Therefore, we have considered the example anisole, wherein you can see oxygen bonding with aryl group will be a partial double bond. So therefore, it is going to be broken down to give phenol and then alkyl halide. So next, let us see electrophilic substitution reaction. So alkoxy group of aromatic ethers is ortho and para directing and activates the aromatic ring towards electrophilic substitution reaction. It is same as phenols. So here alkoxy group is present and attached to the aromatic ring, wherein it has lone pair of electrons. So lone pair of electrons are shifted to the adjacent bond and the pi electrons are being shifted to the adjacent atom. So therefore, when lone pair of electrons from oxygen atom is being shifted, that is delocalized, it possesses positive charge along with the double bond and the atom will have lone pair of electrons in the ortho position. Now in this way, delocalization of electrons takes place in ortho and para position. So lone pair of electrons in ortho position will shift to the adjacent bond, creating double bond here, and therefore electrons, that is pi electrons, will shift to the adjacent bond, making it negative charge, showing it as lone pair of electrons. And then this lone pair of electrons will shift to ortho position again. So delocalization of electrons takes place within the aromatic ring, which is directed by oxygen in the alkoxy group. So this is the resonance structure of ethers. Next is, let us see the electrophilic substitution reaction, various types of reaction. In that, first one is halogenation. So phenyl alkyl ethers undergo usual halogenation in the benzene ring. So example, anisole undergoes bromination with bromine in ethanoic acid even in the absence of iron 3 bromide catalyst. So it doesn't require any type of catalyst. So it is due to the activation of benzene ring by the methoxy group, that is going to produce para isomer, and then it is about 90% yield. So anisole with bromine, it is going to be in the presence of ethanoic acid. It doesn't require iron 3 bromide as a catalyst. So it is going to form para-bromo anisole, along with that ortho-bromo anisole, and then hydrogen bromide. Next is Friedel-Crafts alkylation. So anisole undergoes Friedel-Crafts alkylation, that is, the alkyl group is introduced at ortho and para positions by reaction with alkyl halide in the presence of anhydrous aluminium chloride. So it is a Lewis acid which acts as a catalyst in this reaction. So here is an example, that is anisole with methyl chloride in the presence of aluminium chloride. So it is going to produce 2-methoxy-toluene, and along with that 4-methoxy-toluene as a product. Next is Friedel-Crafts acylation. So when anisole is treated with acetyl chloride in the presence of anhydrous aluminium chloride, it is also going to form ortho and para acetyl derivatives of anisole, and then let us see the reaction. So anisole with acetyl chloride in the presence of anhydrous aluminium chloride, it is going to form 2-methoxyacetophenone, along with that 4-methoxyacetophenone. So here it is in a ortho position, here it is in a para position. Next type of reaction is nitration. So anisole reacts with a mixture of concentrated sulfuric acid and concentrated nitric acid to form a mixture of ortho and para nitroanisole. So anisole in the presence of both a mixture of concentrated sulfuric acid and the concentrated nitric acid, it is going to produce 2-nitroanisole. So nitro group is in ortho position, then 4-nitroanisole, here nitro group is in para position plus water molecules. So that was about the chapter alcohols, phenols and ethers. I hope you have understood. So thank you.